This chapter looks a little bit more specifically at the details of some feedbacks that we implied when we looked at the perturbations and responses in the past climate. We learned a lot about what could be relevant for global warming. Here we will look at all the recent changes and some modeling studies and so on that will get into the details of some of the feedbacks that are really relevant for contemporary climate. And again, keeping in mind that climate sensitivity is not just about doubling CO2 and looking at the warming, but also the Earth system feedbacks. We will get into the specifics of some feedbacks that are relevant for where we are headed and why we should worry about some of them. So we discussed the feedback processes that determine the nature and rates of climatic change in response to climate forcing. Obviously, we are the big forcing now. We explained the differences in the characteristic behavior of biophysical and biogeochemical feedbacks. So we'll make a distinction between the two and describe the means by which the feedbacks can be identified using models and or observational data. As we implied before for paleo reconstructions, the data is never really always sufficient for detailed diagnosis of the processes and feedbacks, but many times feedbacks are implied which can be completely understood in terms of process bases for these feedbacks using models. So the strength also needs to be quantified, because as we are perturbing the system now heavily with increased greenhouse gases, we want to know how much amplification is possible. Okay, this is necessary for predictions of the future, which actually started way back in the 1800s when Svante Arrhenius was already talking about the influence of acid in the rain in the air upon the temperature of the ground. So he was already concerned about the CO2 emissions from the coal burning and other energy uses, biomass burning, etc., because of the industrial activities following the Industrial Revolution. And he had even thought of projections thinking about change in greenhouse gases resulting in temperature changes and changes in water, atmospheric water vapor. And he specifically talked about carbonic acid. Much later we talk about we experienced so-called acid rain impacts on amphibians as indicator species, and then moving much more into all the other related Earth system feedbacks. We have already estimated the radiative forcings relative to 1750, which is the beginning of the Industrial Revolution with the steam engine, and then whatever followed in terms of how to use that for various applications of large-scale industrial activities. Radiative forcing here is again the additional imbalance of shortwave and long wave created at the top of the atmosphere, because that's what perturbs the climate. And level of confidence is indicated here. Some things have low confidence, like cloud adjustments due to aerosols. We already mentioned that aerosols have a direct effect where they can scatter or absorb sunlight, but they also have an indirect effect where, as we discussed a few times, affect cloud properties. In addition to being cloud condensation nuclei, they affect the droplet sizes, so rainfall amounts and distribution. They are argued to affect, of course, ocean primary production, but also hurricanes and so on, monsoons, etc. So the understanding is still kind of low of these indirect effects, so the confidence is low. Some are very high, like the impact of CO2 forcing, which is about 1.68 watts per meter meter squared compared to the amount of accumulated CO2 over this period. But you can see the range is also very high, from 1.33 to 2.03. Methane with its drivers has about 1 watt per meter squared, and you have ozone, CFCs and HFCs, N2O. We'll look at these more specifically in terms of their feedbacks. Carbon monoxide, non-methane volatile organic carbons. So volatile organic carbons act as precursors for various things like CO2, methane, ozone, and so on. NOx emissions from vehicles, fossil fuel burning, include nitrate, methane, and ozone. And there is albedo change due to land use, which has a cooling effect, just like potentially the impact of aerosols on clouds, for example, by increasing cloud brightness temperatures, which is shown here as negative, but you can see the range, the uncertainty is remarkably high, but it still remains within the negative range. So it's a cooling effect, net cooling effect. Solar radiance is a small positive forcing in the modern times, not even remotely close to explaining global warming, as has been tried to argue by some people. Total anthropogenic radiative forcing relative to 1750, then 1950, 1980, and 2011. You can see that the total radiative forcing has gone up, but the uncertainty is also large. The confidence is high. Back to 1950, it's a reconstruction, so confidence is a little bit lower. We will look at many feedbacks along the way, and we will mention which one are quite well understood and what we can say about their impact going into the 21st century, and what it means for the global warming targets and so on. The main ones we have looked at, of course, are ice albedo feedback, lapse rate feedback, water vapor feedback, and cloud feedback, which didn't include carbon cycle feedback, so we will look at those details. Lapse rate feedback basically looks at unperturbed profile. We have warmer temperatures at the surface. A main consequence of greenhouse gas effect is to increase surface temperature, as you remember from the energy balance. And we go up to the tropopause. There are also perturbations to the stratosphere. But we will worry about the lapse rate in the troposphere, because that determines the changes in the weather and climate response. You have a radiative forcing of delta Q. If it is a shift uniform temperature range over the vertical, then you have one potential response to climate perturbation or radiative forcing. You can have larger temperatures changes in the atmosphere in the upper troposphere, or larger changes at the surface. In this case, you will get a negative lapse rate feedback because you are you are basically making for it for the atmosphere easier to convect, whereas here you have positive lapse rate feedback. So it depends on whether you have a negative lapse rate feedback or positive lapse rate feedback. And we will not really revisit this too much because it's part of the whole cycles that we will look at in terms of what happens to vegetation, what happens to carbon cycle, what happens to carbon uptakes in the ocean and the atmosphere, and clouds and so on, but not so much specifically into the details of lapse rates themselves. So I will return to climate sensitivity in the next podcast. I hope you get a sense of where this chapter is headed, as we will see many more specific feedbacks in the system, but now focus very much on what are relevant in the contemporary climate, unlike the last chapter where we went back into time and looked at Paleocene, Eocene thermal maximum, the Eemian, the last deglaciation 12,000 years ago, last glacial maximum 21,000 years ago, and so on.